considering the words that make up the name of this classifier, I am sure that something identical with this image has been formed in your imagination. The image that should have come into your mind is this. Random forest is a classifier that consists of many classification trees. In order to classify a new object, the vector which contains the object must be put down each of the trees in the forest. Each tree returns a classification result which represents a vote for that class, from all of which the most voted class will be the result exported from the forest. To understand how random forest works, it is important to have knowledge of the structure of a classification tree. A classification and regression tree, also known as decision tree, is a way of classifying different objects according to common elements. It represents rules, which can be understood by humans and used in knowledge systems, such as databases. It is responsible for giving an ensemble of distributed data. As an example, you can think over the outcome of a game between two basketball teams. Let's consider some variables such as the location of the game, the starting time, the playing position of a specific player, the characteristics of that player. On the one hand, each non-leaf node of the tree is a test and its edge partitioning the variable into subsets. On the other hand, leaves represent the possible outcome, as you can see. Giving a decision tree the necessary characteristics of an observation, it tries to find if the observation coincides with an existing category or not. In the case of dependent and classified variables, the algorithm returns the classification tree, else in the case of continuous variables, the algorithm returns a prediction tree. One of the greatest features of such a tree is accuracy, where the possibility of making a mistake is minimal. In 1984, Bryman suggested 3 procedures of determining the accuracy of a cart. First of all, to determine the accuracy of a classification tree, it is important to create the tree, using X, where X stands for the vector of variables that describe each observation. In addition, X represents the error rate of the classifier, and finally, L is the sample data being used for constructing the tree. One of the ways used to calculate the accuracy of the classifier uses the L sample of data, also known as the training set, and specifies the error rate by testing the accuracy using observations whose class is already known. The second way is usually applied when the training set is large. By dividing the set into randomly separated groups, L1 and L2, we use the first one to train the classifier and the other one to test it. Using those two groups, we can calculate the error rate. The third and final way to calculate the accuracy of a classifier is strongly recommended for small training sets. For a start, the training set is being separated equally into K groups. Then the classifier is being trained using the K1 groups, and the last one is used for testing. Next, the error rates for all K groups must be estimated using the algorithm referred before, so that in each case all of the groups will want to represent the testing set. Now that we have discussed all you need to know about classification trees, we can move on revealing more information about random forest. Most of the options that concern the specific algorithm depend on 2 data objects generated by it. While a tree is being grown, its training set is drawn by sampling with replacement. This results to having the 1/3 of the cases left out the sample. Using this out-of-bag data, as it's being called, we can get a running unbiased estimate of the classification error as more trees are added to the forest. We can also get estimates of the variable importance of each problem. Regarding to the error estimate of random forest, it is important to refer that each tree is constructed using a different bootstrap sample from the original data. As we said before, the 1/3 of the cases in the sample are not used in the constructing phase of each tree. Next, we put all of the out-of-bag cases down the tree in order to get for each of those a classification. In this way, a test set classification is obtained for each case in about the 1/3 of the trees. Finally, by taking the most voted class, let's call it J, every time case N was out of bag, we can calculate the error estimate by taking the proportion of times that J was not equal to the true class of N averaged over all cases. In addition, to calculate the variable importance, we put the out-of-bag cases down in every tree in the forest and count the number of votes cast for the correct class. The next step is to randomly permute the values of variable M in the out-of-bag cases and put these cases down the tree. by subtracting the number of votes in the correct class in the variable m permuted out-of-bag data from the number of votes for the correct class in the untouched out-of-bag data. We can export the raw importance score for variable m by taking the average of this number over all trees in the forest. When the number of variables is very large, forest can be run the first time using all the variables available and the second time using only the most important variables exported from the first run. Moreover, it is important to mention and analyze the impurity of a tree. Impurity of a tree is the sum over all terminal nodes of the impurity of a node multiplied by the proportion of cases that reach that node of the tree, and it is used to decide what split criteria to use each time. The most widely used measure of impurity is Gini index. Every time variable m is used to split a node, the Gini impurity criterion for the two descendant nodes is less than the parent node. Adding up the Gini decreases for each individual variable over all trees in the forest gives a fast variable importance that is often very consistent with the permutation importance measure. For example, to calculate the impurity of a tree with one single node and two variables a and b with both having 400 cases, we can calculate the Gini index to be 0.5. After calculating the Gini index, we are able to select the next split by taking the one which most decreases the Gini index. This is done by over all possible places for a split and all possible variables to split. I'm sure that you are now wondering when it is time to stop growing a tree in random forest. There are many possible answers, such as, stop when reduction in impurity is smaller than a threshold, stop when the leaf node is too small, or hypothesis testing. As we have discussed before, out-of-bag data is one of the objects generated by random forest. The second object is called proximities, which form an NXN matrix. They are useful tools for replacing missing data, locating outliers, and producing illuminating low-dimensional views of the data. Additionally, proximities are computed for each two pair of cases by running all of the data down the tree. When two cases occupy the same terminal node, their proximity is increased by 1. At the end of the run, it is possible to normalize the proximities by dividing by the number of trees. Many users noted that they could not fit an NXN matrix in fast memory when dealing with large data sets. To come up against such cases, a modification was made in order to reduce the required memory size to NXT, where T represents the number of trees in the forest. As we said before, random forests use proximities to replace missing data both in training and test sets. Regarding to the training set, there are two ways of replacing missing values. The first way is fast. If the current variable is not categorical, the method computes the median of all values of this variable in class J, and then it uses this value to replace all missing values of that variable in class J. Otherwise, if the specific variable is categorical, the replacement is the most frequent, non-missing value in class J. These replacement values are called fills. The second way used when replacing missing values in random forest is computationally more expensive, but has given better performance than the first, even with large amounts of missing data. It replaces missing values only in the training set, beginning with a rough and inaccurate filling of the missing values. Next, it does a forest run and computes proximities. If x, m, n is a missing continuous value, its fill is estimated as an average over the non-missing values of the m variables weighted by the proximities between the case n and the non-missing value case. In the case of a missing categorical variable, replace it by the most frequent non-missing value, where frequency is weighted by proximity. The next step is to construct a forest using these newly filled-in values, then find new fills and iterate again. By experience, 4 to 6 iterations are enough. Furthermore, there are also two methods of replacement for the test sets, depending on label's existence. If labels exist, the fills derived from the training set are used as a replacement, else, each case in the test set is replicated as many times as the number of classes. The replicate of a case is assumed to be class 1 and its fills are used to replace missing values. The second replicate is assumed class 2 and its fills are used on it. This augmented test set is run down the tree, and in each set of replicates, the one receiving the most votes determines the class of the original case. Using human judgment to assign labels often forms the training sets. In some areas, this leads to a high frequency of mislabeling. Many of the mislabeled cases can be detected using the outlier measure. As an example, you can consider the DNA case study. What is more, outliers are generally defined as cases that are removed from the main body of the data. This means that the proximities of the outliers to all other cases in the data are generally small. A useful revision is to define outliers relative to their class. Thus, an outlier in class J is a case whose proximities to all other cases of class J are small. The average proximity, from case N, in class J, to the rest of the training data class J, is given by this expression. The raw outlier measure, represented by the expression you can see on your screens, will be large if the average proximity is small. After that, it is useful to find the median of these raw measures and their absolute deviation within each class. The next step is to subtract the median from each raw measure and divide by the absolute deviation to arrive at the final outlier. These are the most basic information for random forest, which has many applications in genetics, real-time body estimations and many others. To sum up, we are about to see 2 videos of real-time body estimations from Finelli, Gall and Van Gool. Their project was based on random forest because it is a fast and reliable algorithm, which has the capability to handle large training sets in order to estimate the head poses. It is essential for many applications and higher-level face analysis tasks. As the authors said from their experience, in our CVPR paper, we trained a random regression forest on a very large, synthetically generated face database. In our experiments, we show that our approach can handle real data presenting large pose changes, partial occlusions, and facial expressions, even though it is trained only on synthetic neutral face data. We have thoroughly evaluated our system on a publicly available database on which we achieve state-of-the-art performance without having to resort to the graphics card. As you can see, the video shows the algorithm running in real time, using as input high-resolution depth images acquired with the range scanner of Wise et al. Thank you all for your attention.